welcome to the second and final lecture of this year's Ihaka Series. My name is Ben Stevenson, and tonight it's my great pleasure to be introducing our speaker, distinguished Professor Adrian Bedevilled. So the topic of this year's series is patterns in space. And I can't think of anyone more suited to giving a lecture on this topic than Adrian, because he literally wrote the book on the subject. I have a copy here, Spatial Point Patterns. And the first thing you'll notice is that Adrian does not do things in half measures. Just look at the size of it. I'll turn it, maybe get a close up. I'll turn it on the side so you can appreciate how hefty it is. This is 810 pages crammed full of material on spatial statistics. When I look at Adrian's publication record, what I notice is that it's similarly comprehensive and far-reaching. He's published quite mathematical papers pertaining to theoretical results relating to spatial statistics. He has published methodological papers describing new ways of analysing spatial data, and he has also published applied papers describing analysis of real data using statistical methods, often those that he has come up with himself. So to me, his publication record is impressively traverses all the way from the theory right through to the practice and the application of spatial statistics. Arguably, however, his biggest contribution is not through his published papers, but instead through his software development. He is the maintainer and lead author of what is arguably the most comprehensive software package available in the world to fit statistical models to point pattern data. That's the R package spatstat. Spatstat is just as comprehensive as his book. If it's described in this book, you can do it in spatstat. Consequently, it's used all over the place. It's been cited, the SpatStats package has been cited in over 3,000 research publications, and it's also widely used outside of academia and outside of research. So what Adrian has achieved is he has brought cutting-edge spatial statistical methods to the masses. You can go home tonight and you can fit a spatial model to data using the latest and greatest methods, free of charge, all thanks to Adrian. So when I was lucky enough to talk to Adrian earlier this week, and I asked him one thing. I said, is there anything you would like me to say when I introduce you? And he said, could you let everybody know that I am retired? So everybody, Adrian Bedevilled is retired, which means we are ever so lucky to have him with us tonight, all the way from Perth, Australia. Please join me in warmly welcoming him to give his talk called Connecting the Dots with R. Over to you, Adrian. Try again.
Okay. Testing?
We're good.
What was I saying? It's lovely to be here. It's lovely to see so many familiar faces and new friends. And it's a great honour for me to give a lecture in the Ihaka series. I think this is a really good thing to do. Celebrate your achievements, Auckland University. It's well worth the trip of whatever it was, 4,000 kilometres, to show you a few of the things which I do. Okay, so let's see if I can make this work. Okay, passed the exam. Okay. All right, I want to give you a sense of history, because these things don't just happen overnight, right? Technology doesn't just happen overnight. So I'm going to start a long way back in 1854 in London, when there was an outbreak of cholera. And at that time, cholera was a terrifying disease because no one knew what it was or how you got it. There were a few theories. The popular theory was wrong. It was that you got it by contaminated air. There were some people who suspected that it had something to do with contaminated water. So a doctor called John Snow collected evidence from other people and produced a map of the home addresses of the cholera cases in this particular outbreak. So if you look closely, you can see little histograms at each address that show you how many people there were at each address that were stricken with cholera. Here's a cleaned up version of the same thing, where the red circles are cases and the blue symbols are the water pumps. So in those days, people got their water from a mechanical pump that drew water from the ground. You didn't have plumbed town water. And the point that Dr. Snow made was that the people afflicted with cholera were closer to this pump in the middle, the Broad Street pump, than to any of the other pumps that you see in the picture. So that provided really important evidence that it probably had something to do with contaminated water. It turned out that that water pump was contaminated, and that began the whole Victorian era obsession with hygiene. There were so many consequences that came from this one graph. Okay, something closer to my home. Here we are in New Zealand, over in Western Australia where I live. There's an area in the middle of the state about here called the Murchison region, where there's a lot of gold. So here's a map resulting from a geological survey where the blue circles are gold deposits, the red lines are major geological faults, and the green colour is a particular rock type called greenstone, which is associated with gold. So what we're trying to do by making this survey is to figure out what kinds of conditions are favourable to the appearance of gold deposits, and basically where should we dig. So they call that prospectivity. Where's the most likely place that you should consider digging for gold? Another example from Africa. Here we are zooming in on Tanzania. On the right there is the mighty Kilimanjaro. The left is the Serengeti Plain. And about halfway between is a gorge, a river gorge called Olduvai, which is a place where ancient human remains have been found. So if I continue zooming in, eventually we'll come to this research area where scientists are patiently, with paintbrushes and everything, painting back the layers. They're down to about 2 million years old. And in this layer, they can find fragments of stone that have been used as tools to process prey, basically to take meat off the bone of prey. So here's a map that these scientists produced. Each little cross there is a stone tool. And what we're trying to do from that is to figure out how these ancient humans processed their food. How did they live? Easy, right? This is all the evidence we've got, and somehow we've got to figure out how they lived, how they ate, how they processed their food. Simple. Another example. Here is a picture from a radio astronomy survey of the sky. Each dot there is the sky position of a distant galaxy. And in this particular area, there's about 4,000 galaxy positions that you can see there. And what we're trying to do is figure out, well, basically explain the universe, explain the distribution of the universe. How does it come about that there are these intense concentrations of galaxies in particular places? So what these examples all have in common is that they're all maps of something where, locations where something was observed or an object was found. So we call that a spatial point pattern. And the problem I want to talk about is how to analyse a spatial point pattern. Now, humans have this, give someone a picture and they immediately start drawing on it, you know, and so there's a terrible tendency to just say, I'm going to measure the distances between the points, or I'm going to, count the number of points that do something. But that's not how a statistician thinks about it. We have to have a reason. We have to be able to defend what we're doing. It has to be defensible. So we have to follow good statistical principles when we analyse any kind of data. So statisticians love models, right? Everything we do is related to models. The fundamental objects of statistical science, I would argue, are models. A model is a statistical description of how the data were generated. So, for example, with the stone tools, we could say, well, the stone tools were scattered randomly over the ground, independently of one another, with uniform kind of density. Now, that model might be true, it might not be true, but it's a model, it's an example of something we could debate. Is this model appropriate or not? Okay, so in the simple recipe for analysing data is, first of all, find out about the background, then formulate a model, formulate some kind of statement that you think might be true about the data, and then fit the model to the data, and then check whether the model seems to be a good description of the data. And if you're happy with that, then draw conclusions or predictions from the model. So we don't just take, numbers or data and just put them through the ringer and come out with the number, 42. We have a principled process where we think of a possible explanation for the data, and then check that that might be a good explanation, and if so, then we draw conclusions. If we don't like the model and we go back to square one, think of a better model, do the whole thing again. The modelling cycle. Okay, so simple example. I just need to use this for reference later on. I've got some numbers, let's call them x and y appears to be related to x. So what do we need first? A model. So let's think of a model. We could say, okay, I think that the data are randomly scattered around a straight line. So there's a straight line relationship, and the actual data are kind of scattered around that. Okay, that's my model. Next step is to fit the model to the data. In this case, that means draw a line through it, because we think there's a linear relationship. So we find the line of, let's say, best fit. That's called linear regression. That's just the name it has. Then the next thing is to validate the model. So we could, for example, measure how much the data actually disagree with the line. Those are called residuals. They could be positive or negative. Differences, vertical differences between the data points and the line. And then if we just look at those residuals, plotting them against x, what should be left there is random scatter, because we assumed that there was a random scatter around the line. Well, that doesn't look exactly like random scatter to me. It looks like that cannot be described as a completely random scatter. So there's a bit of suspicion there. So then we have various ways of checking that the model seems to be right. And one which I particularly like is the influence, or likelihood influence. So what I've done here is I've replaced each one of those data points by a circle, and the bigger the circle, the more anomalous the observation is, right? So the big circles down here, and rather big circles here, suggest that those data points don't agree with the line, or they're anomalous in some respect. So, okay, it's beginning to look as though a line was not a good model. Almost, but not quite good enough. So what we could do is then go back to square one, formulate a new model. So let's say, okay, the points are randomly scattered around a curve, and the curve is approximately straight. Okay, so then we fit the model. That would be local linear regression, for example, and so it goes. So that's the kind of cyclic process that we want to be able to do with any kind of data, I would argue. Okay, so how do we do all that stuff? Well, it used to be really, really hard. I can tell you, young folks, it used to be really, really hard to do all the stuff I just described. Coding, programming, had to do all yourself. Then along came statistical packages and statistical environments, and thanks to several of the people in this room, and one in particular, we have this marvellous thing called R, which is a kind of framework for allowing you to do all these kinds of things. So in R, if I wanted to do what I just described, you can almost do it with, it's almost like 16 characters to do each one of those things. So if I say lm y tilde x, if y and x are names that represent where the data is kept, then lm, linear model, that's a tilde, it means that y depends on x. So if I just type that, that performs a linear regression. I mean, it's almost, it's almost like texting with one thumb, incredibly efficient. And if I want to save that or, record, keep that somewhere, the result somewhere, I just use this, this is the left arrow which says assign the result of that to this object fit. So then fit is now an object that sort of contains the fitted line. And if I say I want to see that, print it, or plot it, I just say print fit, plot fit, etc. And if I say residuals are fit, it'll calculate the residuals like I was talking about, and these other things that I talked about, influence and so forth. So this is like a really, really easy way to talk to the computer and say, I want you to do that, now show me that, I don't like that, go back and change it. So if I decide I want to do local linear regression, I just have to remember what the name is of the thing that does local linear regression. Cool, really easy. Okay, so back to spatial point patterns. So my question is how to analyse a spatial point pattern using the same kind of approach, right? An approach which can actually be justified. First, I come up with some assumptions, a reasonable model, then I fit the model to the data, and then I can criticise whether the model is a good one or not. So I want to do this analysis using good statistical principles and with some practical software. Like I don't want to be sitting there all day just coding, right? Okay, so the first thing we need is a model. So the name for that is point process. Point process is the technical word we use to talk about a model for spatial point patterns. So here's, think of it as like a machine that makes carpet squares, right? And each time you press a button, it makes another carpet square with a different pattern on it. And I want to be unique, so I don't want any of the carpet squares to look like each other. So each time you press the red button, out comes another carpet square with a different pattern on it. So the machine that makes the carpet squares is the point process, right? An individual carpet square is a point pattern. All right. So in particular, there's one called a Poisson point process, which is where the individual points don't depend on each other. So it's like you splatter them down and they don't care about each other. Each point is put down randomly without looking at the other points. That's called a Poisson point process. I won't bore you with the reasons. Okay, so the verbal way to say that is points are scattered completely at random. Okay, so by the 1960s, there was a well-developed theory of these spatial point processes. There was like a nice theory, and there were these Poisson point process models that I talked about. And there were also physicists who'd invented models to describe gases, like where the molecules in a gas keep away from each other because forces push them away from each other. And then also some statisticians had developed models to describe the clustering of galaxies, where the galaxies tend to stick together or to be close together because of gravity or whatever. So these kinds of models had been developed. So this is the point where I became aware of this. I thought this was really cool. I want to do this. So I signed up. So here's me 50 years ago going off to, leaving Australia to go to the University of Cambridge to study, at the feet of the great and wise about, point processes, right? So if you want to learn from the masters, you have to go through the solid foundation. So you have to get this solid theoretical foundation first. Okay, so there's a thick book, even thicker than that one, where you can learn about point process theory. Open it at page 1 and you realise pretty quickly, oh dear, this stuff is, okay, it's fundamentally powerful mathematical stuff, but it's also pretty complicated and abstract. So here's page 1, definition. What is a point process? A point process is a random element of the Polish space frac n of integer valued measures on the Borel sigma field of R2. Okay? So, okay, eventually you can figure out what it means, but decades later I realised this is a useless definition. It's like saying, yeah, a TARDIS is a box that's bigger on the inside and can travel through time and space. It's like it doesn't tell you how to make one or even how to drive one. So, thanks, pure mathematicians. If a TARDIS ever materialises in my garden, I'll know it's a TARDIS. But it's not useful for any statistically practical purposes, really. I mean, I'm exaggerating, but it is a rather remote concept. So let's backtrack a bit. Let's go to page 10 or whatever and get past all the scary stuff and look at some of the concepts that eventually calm you down a bit, and basic concepts about a point process. So the first one that arises is the concept of intensity. So intensity is like basically how hard it's raining is how I describe it. Okay, so the picture on the left here has low intensity because there's not many points per unit area. The picture in the middle has high intensity. There's more points per unit area. And this picture on the right has a gradient from low to high intensity as you go from left to right in the picture. So you can have non-uniform intensity. So intensity means basically the density or the number of points per unit area. Okay, so that's something we can apply in practice. You can take, for example, the stone tools data, and we can infer from this data set what the intensity of stone tools was likely to have been, okay? So to do that, I'm going to use kernel smoothing. So if you don't know what kernel smoothing is, imagine each one of these stone tools is replaced by a square of chocolate, and then you just put a hairdryer over it until it melts slightly. That's a kernel estimate. So what you get here is, that's a colour picture of it. Here's a sort of perspective view of it. See what I mean? It's like a surface where higher values mean more points per unit area. So back here we can see from the colour scale, so these peaks here, there was about 14 or 15 stone tools per square metre. And in the other areas there was as few as one or two stone tools per square metre. Okay, so that's intensity. So we had the idea of intensity and we had this Poisson process. Let's put them together. So this is, I got my machine, my carpet square machine, to make 6 carpet squares using the 2 rules. First, the intensity surface. The intensity surface is the one I got from the data. And the Poisson process, so the points don't pay any attention to each other. So let me explain that again. The machine was configured so that the density of points has got this particular spatially varying trend, but the points themselves ignore each other. Points themselves are independently random. So what's common to these 6 pictures? Well, they all have the clustering of points at the same places, right? They all have these concentrations of points at the places that were identified from the original data. Okay, cool. The second concept I want to talk about is interaction. So interaction is basically whether the points care about each other. So in a Poisson process, the points don't care about each other at all, and sometimes they happen to be close and sometimes they happen to be far away, completely at random. In a point process where the points don't like each other, like a model for molecular gases or something, the points like repel each other and keep away from each other. So that's the kind of picture that would be suggested by, the kind of model that would be suggested by this picture. On the other hand, you could have clustering. So for example, the seeds that fall off a tree tend to be clustered near the tree. And this produces situations where the points tend to be found close, near to each other. Okay, so back to the stone tools. I could assume that the actual intensity of this picture is constant. So the density of points is constant, but that the points like each other. So whenever a point is there, then another point wants to be there as well. So when you do that, okay, sorry, 40 years passed from the previous picture to this one. Okay, so now we know how to do this, but this is a picture showing what would happen if I assumed that the intensity was constant, the points interact with each other in a clustered way, and then I got my carpet square machine to produce 6 outcomes of that process. So that's a process where the intensity is constant, but the interaction between the points is attractive. They like to be together. So in these 6 pictures, the clusters of points are in different places, right? Because that happens kind of at random. So just to show you the difference, this is a previous one. This is a Poisson process where the intensity is spatially varying, but there's no interaction. The points don't care about each other. In this other picture, the intensity is constant, there's no spatial preference, but the points like to be close together. Okay, so which is it? So this is a problem. So in 1964, great statistician Maurice Bartlett proved that if you only have one point pattern, you can't tell. It's impossible to tell whether your point pattern has spatially varying intensity or clustering. Does that make sense? Okay, this is a really earth-shattering discovery. So a model, in technical terms, for the technical people who are still awake, a model which has both of these features is unidentifiable, so you cannot determine which of those features is present. So that is really a problem, because it means, for example, suppose we've discovered some new disease. If I just have a map of the disease cases, I cannot tell whether a cluster of cases is caused by a localized source, like the cholera, contaminated water, or whether it's caused by contagion, like where the cases tend to, you tend to pass it to somebody who's near you. So these two things, localized source of disease, of a pathogen, or contagion of the pathogen, cannot be distinguished. In principle, like mathematically, there's a theorem that says that it's impossible. Right, so it's kind of depressing to discover that when I was this old, someone had already proved that it was impossible, what I was trying to do was impossible. That's kind of depressing. Okay, so this is a roadblock which really bothered people. So by the late 1970s, some experts had concluded that you cannot use standard statistical methods to analyse spatial point patterns. So what we're trying to do, what I described the agenda at the beginning, cannot be done. And there were technical reasons. They would say the likelihood is intractable. There were technical reasons as well as that. Intractable, that's one of those words that experts use to hide the fact that they don't know something, right? It's like if you go to the doctor and he says, oh, you have idiopathic something or other, or cryptogenic something is another one. That just means they don't know, right? So intractable means they don't know how to make it work, all right? So I talked about unidentifiability. Bartlett's theorem tells you that the realistic models cannot be disentangled. And people concluded that this means that you need more restrictive assumptions. You need to simplify the problem to make it work. But that is deeply troubling, right? Because what you're saying is somewhere in the universe, there's a field of application where statistics doesn't work. That cannot be true. Please, that cannot be true. All right, so, okay, so physicists love to talk about this. The great challenge of science is the grand unification of the fundamental forces of nature, right? I make a big deal about it. Now, in statistics, we're not quite so grandiose, but we also have this idea of the unification of statistical models. So although statistical models are all sort of different things, we have this idea that they can be brought together under, simplifying umbrellas. So in the middle of the 20th century, linear regression, which I talked about, and several other methods were brought together under one heading called the general linear model. And what this meant was instead of having like 10 chapters of a book, that was compressed to one chapter, And you could deal with all these problems using basically the same ideas and the same software. So together with this theoretical development, people develop software. And that has always happened, right? Whenever there's a new idea about statistical methods, someone works on software to make it work. So GenStat was and is still a statistical package which did this, brought these different models and tasks together in a single software unit. Then about the time I was in Cambridge, so 1980s, logistic regression, Poisson regression. So I think I mentioned logistic regression before, but there were several other kinds of models that were brought together under the same roof called the generalized linear model, and a separate piece of software was developed to do that. So this is really exciting because it means basically the book of things you have to learn is getting shorter. Right? You only have to think about the general concept. You don't have to learn the detail of each of these individual ones to understand what's going on and to be able to drive the software. So what? Now suddenly you're saying you can't do it? You can't do it for point process models? We cannot take this agenda any further? That's really shocking. So there's a paradox. So there's a powerful general mathematical theory of point processes, which has existed since I was in short pants. This is clearly the correct mathematical foundation. You stare at it and you realise it's the right way to go. But no one can understand it, or no statistical applied statisticians can cope with it, and even experts find it intractable for many applications. So that's strange. Usually, I mean, if you, at least when I was taught statistics by some very mathematically powerful people, they always emphasize that you have to understand the underlying mathematics first and then everything will be good. That's not happening. The mathematics is there and it's not helping us somehow. Okay. So the message that went out to other scientists, non-statisticians, other people who had relied on statistics for many things up to that point, was that statistical methods don't work for this problem. So it's like we're abdicating, almost like we're abdicating authority or something over this particular field. So scientists shrugged their shoulders and started looking beyond statistical science for solutions. So they started, these are some of the headings under which alternatives to statistical methods were developed. I'm not minimizing that. I mean, really important and good work was done, but somehow the background assumption was we can't do this using statistical methods. So there are various things I won't insult everyone in the room by, I'm not trying to do that. I'm just trying to say the message that went out was that statistics doesn't work. Okay. So what the statisticians could have done was they could have developed practical methods for fitting the Poisson models, because if you assume that the points are completely random, as in the Poisson process, then everything does work. They could have dealt with situations where you have more than one point pattern. Goodness me, like think of, here's an example where an entomologist took photographs of these little insects called water striders that sit on the surface of a pond. And they obviously are territorial, they don't like to get too close to each other. Since we have 3 photos, we can easily see that it's the insects being territorial, it's not. So suddenly this is identifiable. We can identify that the common feature of these patterns is that the insects stay away from each other. So that is identifiable, that's not a problem. So Bartlett's theorem doesn't apply if you have more than one point pattern. There are things where a lot of progress was made. Space-time point patterns, so if you know not only the location but also the time when something happened, like an earthquake, right? If you have earthquake data where you know where and when the earthquake happened, then you can make progress and you can do statistical analysis. And it would be remiss if I didn't mention 2 important names. The late David Vere Jones was a great New Zealand statistician and his collaborator Yoshi Ogata from Japan. No accident that someone from New Zealand and someone from Japan are working on earthquakes. Really important, really valuable, really good models that they came up with. So that does work. And case control. So the other example is if I have a map that shows me the home addresses of people with the disease and other people without the disease. It's called a case control data set. In that case, you can deal with those data and get useful information. So the only case that doesn't work is the one I described. So the idea that stats doesn't work is a bit silly. So I can't help feeling, oh yes, okay, so now I watch a lot of YouTube. So now I want to tell you about this one simple hack that they don't want you to know. Right, like and subscribe. So, so 1971, Washington DC, there was a Congress of the International Statistical Institute. That's like the Olympics, I guess, of statistics. And there was a session in the conference called Statistical Problems in Geology. And two geologists, Fritz Achterberg and S. Robinson, showed a picture like the one I showed you before, a geological survey, where you've got gold deposits, geological faults, and some other things, and asked, well, how can we determine conditions that are favourable to gold, and how can we find where to dig? So in these sessions, someone gets up and gives a lecture, and then someone else responds. It's called the respondent or the discussant. In this case, the discussant was some guy called John Tukey, great American statistician, and he came up with the following idea. I don't know, why don't you cut the region into little squares, pixels, and then give each pixel a value of 1 if it contains a data point and 0 if it doesn't, right? So you end up with a big array of zeros and ones. So you've turned your point pattern into a huge array of zeros and ones, with a 1 representing the presence of at least 1 point in the square, right? Then you've got some predictor variable, like we have something we're going to use to predict the presence of gold. That's some other variable, so we get a value of that variable for each pixel as well. So then we have y, which is zeros and ones, telling me yes, 1 if there's a point and 0 if there isn't, and we have some other predictor variable that we're going to use. Then we do logistic regression, which is where you fit a kind of relationship between y and x. Y is either 0 or 1, so instead of fitting a straight line, you fit this so-called logistic curve, where the yellow curve is the probability of getting a 1 as a function of x. So then you can predict the probability of a deposit, the probability of presence of a point as a function of the explanatory variable x. Let's try it for the Murchison gold data. So first we just take the gold points, and I'm taking 10 by 10 kilometre squares. So the square is coloured gold if it's got any gold in it, and it's coloured purple if it doesn't. Right? 10 by 10 kilometre squares. Then, so that's the y. Then for the x, I'm going to take the geological faults, and I'm going to measure distance to the nearest fault. So at each pixel, the colour of the pixel represents the distance from that pixel to the nearest geological fault. Okay? So the top left here is kind of yellow. That corresponds to 120 kilometres. So this point up here in the top left is 120 kilometres from the nearest geological fault, whereas the dark blue, or whatever it is very close to a geological fault. Okay? So that's going to be my x. X is the distance. The value of x at each pixel is the distance from that pixel to the nearest geological fault. Okay, so there's my y and my x. Let's do a logistic regression, and I get this relationship which says that for distances close to 0, so if I'm right on top of a geological fault, the probability of gold is 40%. Whereas as you go further away from the nearest fault, if you get down to say 10 kilometres, the probability is less than 10%. So here's a picture of the fitted presence probabilities. So using this model, simple model, which says that the probability of gold depends on distance to the nearest fault by some simple relationship, we get a picture like this, showing that in some places the probability of gold is as much as almost 50%. Cool. So Tukey, this was brilliant, right? I think it's really brilliant. It was not really understood at the time. So fitting a logistic regression is approximately the same as fitting a Poisson point process model. So this is, Tukey explained in 20 minutes to geologists how to fit a Poisson point process model with a particular form, and they could go away and do it themselves. It's just brilliant, genius. It's brilliant because you can use existing software to do it. And like, it's also deeply brilliant because all that stuff about integer valued measures, that's what's going on. The pixelated point pattern is basically an integer valued measure, or it's a conceptual way to think about an integer valued measure. So all that obscure mathematical description is actually, if you deeply understand what that is, like Tukey did, it's the same concept. So this was a brilliant insight, and it should have, so this is my second paradox, this should have led to enabled statisticians to make big contributions to, geology, ecology, epidemiology, astronomy, so forth, immediately, like in whenever it was, 1971. That didn't really happen. For some reason, people didn't see that as quite as insightful as it is. And instead, it was Fritz Achterberg, the geologist who pioneered this thing, called it spatial logistic regression, developed the whole science of mineral prospectivity analysis, became quite wealthy. The science became quite wealthy. And eventually this technique spread across the whole of science, and the connection with statistics was forgotten. So I've met people who said, oh no, I don't use statistical methods, I use GIS regression. Which is that, okay? So there are people who are convinced that this is a non-statistical technique. So the connection with stats has been completely forgotten. So it reminds me of this cartoon from Larson. It's like, what are we doing? This is fundamentally, we're not looking at what's in front of us. Okay, so there were a few, I'm being very unfair, there were a few statisticians who pursued Tukey's idea, his former student David Brillinger, and a few other people, including several Australians, and Rolf Turner, who unfortunately can't be here today. Hi Rolf, if you're listening. And developed practical algorithms for fitting these models. So gradually, the statisticians caught up with where they should have been. I mean, back in 1971, they could have, completely constructed an entire science of spatial statistics and solved a lot of problems that were important to scientists at the time. And eventually we caught up, largely thanks to R. So now it's the time to now the message from our sponsor. Where's that book gone? Oh, that's right, it's here anyway. Oh yeah, like and subscribe. So spatstat is an R package that we developed so we said, okay, we're going to make an R package which is going to analyze spatial point patterns using this kind of idea. So yeah, these are the three authors of spatstat. Rolf, who can't be here, Eo Rubak, who's in Denmark, and me basking in the glory. There's a book about it. So we're trying to do the same thing as you do for logistic regression, linear regression, with point processes. So this is how you fit that model, which I described in spatstat. Instead of LM, we have this command called PPM, and everything else is pretty much the same. So if gold is an object that contains the point pattern, the spatial point pattern, and let's say default, for example, is an object that tells you how far away you are from the nearest geological fault, then typing this command will fit that model that I described. And you can print it, plot it. what does it mean to plot a fitted point process model? So this is where you start to have to think, right? Okay, I've got this object, I've fitted the model. Now what does it mean to plot it? So the structure of R makes you think about what these things mean. Okay? So, okay, what should I do to plot a fitted model? Probably draw a picture of the fitted intensity, like one of those colour pictures I was showing you. Simulate, so I have to figure out how to simulate. Then there are these things like, okay, what is the corresponding concept of residuals for one of these point process models? So I've got some data, I fit a point process model to it. I think that the model is a reasonable description of the point pattern, but how do I check? How do I? So a lot of work had to go. So what happened was, thanks to R, thanks to the structure of R, we were forced to think about what all these things mean. What are the residuals of a point process? What is the likelihood influence of a point process? So all these things forced us to think about, or going back and do mathematical theory or whatever it takes to understand what these concepts should mean in the context of a spatial point process. So it actually forced us to go back to the whiteboard and think about what it all means. So here's a selection of papers that we had to use. These are just my papers that were involved in sorting these things out. Now multiply that by 3 or 5 for the people that were, other people that were involved. So a lot of work went into this. So let me show you what we can do. Here's the Murchison data again. And I've taken just a corner of the picture so that you can see some of the detail. So here's what I've done here is I've fitted that relationship again. And here are different ways of fitting the same relationship using different techniques like the non-parametric maximum likelihood estimator and other things, which tend to suggest that, yeah, that's a reasonable model. Then we can do things like calculate residuals. So it turns out that this is the appropriate concept of residuals for this point process model. And the sort of red bump there indicates that there's something happening over here where there are more points than would be expected by the model. So this little cluster of points here, which you can't see because my head's in the way, this little cluster of points here is anomalous in the sense that there's more gold here than predicted by the model. So that's interesting. Here's the counterpart of influence. So remember, influence is something that measures how anomalous a particular observation is. So what I've done, the left picture is the data, the right picture shows circles where the size of the circle tells you how anomalous a particular gold deposit is. So I've got lots of large circles here indicating that there's lots of anomalous stuff happening over here. Whatever that means. So dig there, basically. Okay. So now there's a third paradox I'm going to try and wind up. So, like I said, lots of people went away thinking, both statisticians and non-statisticians, believing that standard statistical methods could not be applied to this problem. So they started looking for other things to do, unconventional alternative strategies. Paradoxically, that was also a good thing to do. It's like, you know, when you're a martial artist and you tie one hand behind your back, it makes you a better martial artist. Same thing here, trying to do things assuming that you can't use standard methods actually led to some amazing new things. So Markov chain Monte Carlo methods, for example, the first MCMC method was an algorithm for simulating one of these point processes. Composite likelihood, that's also was a replacement for one of the things that we thought was intractable, intractable likelihood. So these new methods have also extended statistics itself and made it more powerful. So you can also do these, thanks to these other developments, you can also do things with non-Poisson point process models. So we can fit models in which the points are not independent. The points depend on each other in various crazy fashions. And we can also do all of that other stuff involving other concepts like residuals and influence. Okay, I just wanted to show you this. This is a graph of the size of spatstat. It's about to hit 200,000 lines of code. So that's a lot of work. And there are also lots of wacky tasks that had to be implemented to make it work. I didn't want to implement, but I found that I had to. So we have tortured the letter R in so many different ways. Originally because we just wanted to have a letter R that we could use, and there's all kinds of crazy things that you can do with it. So I'll skip this because that's, once you have the basic idea, you can extend it in so many different ways. But I'm sure you want to see what we can get out of these 4 example patterns. So I'll just quickly summarise what you can do with the available technology. So firstly, surprise, surprise, 175 years later, we've discovered that the overwhelming majority of the cholera cases are in fact nearer to the Broad Street pump. But kind of like using modern methods, we can confirm that and criticise it in different ways and confirm that that was really valid. In the Murchison Gold survey, there are various interesting anomalies going on. The anomalies might represent more productive gold areas, or it might be that someone forgot to map a particular geological fault that should really have been there. It's a bit hard to tell. The Paleolithic stone tools, interesting, because an analysis suggests that different tasks, I mean, there's a bit more data than this because they've actually looked at each stone tool under the microscope. So it appears that different tasks were performed at different places. So it may well have been that the tools themselves were made at one place, by napping off bits of rock, and then used to process meat at another place, which is kind of interesting. The Shapley galaxy concentration, all I can really tell is that there's really intense concentration of mass, and that's still quite a challenge. So just to prove that this is not just old-fashioned stuff, an article recently appeared in the journal Science asserting that they had proved that COVID-19 started in the famous seafood market in Wuhan. And they claimed that they'd done it by genetic methods and statistical methods. And they produced a picture of the early cases, this is from the World Health Organization, early cases of COVID-19 and the Huanan seafood market in the middle. Unfortunately, other things in the middle include the railway station and the research laboratory, which has also been a subject of discussion. So, a statistician called Dietrich Steuern, honestly, it's wonderful. You should read this. It tears it to shreds. So politely tears it to shreds. So this is like, there's a lot of science going on here. It's possible to do it incorrectly. But I just want to summarise what we've learned. So when I was first a student, a PhD student, I was basically told that standard statistical methods are not feasible for these spatial point patterns. That's not true. And I'm so glad it isn't true because, the fundamental principles of statistics have got to work everywhere or they're not fundamental, right? If you have a principle that doesn't work sometimes, it's not a fundamental principle, right? But the other thing that I really want to emphasise is another thing I was taught was if you want to be a good statistician, first you have to do like 3 years of pure mathematics so that you understand the foundations. And then whenever you have a new problem, you should study it carefully from a mathematical point of view, and eventually you'll be able to derive your statistical methods mathematically from those assumptions. So that's not really true either because lots of new statistical methods are invented by thinking about how you're going to compute them. So thinking about the computing is probably more important in some respects. I mean, you have to have some mathematics, right? But it is not the case that statistics is like a corollary of mathematics. That's not how it works. We have to think about how we're going to compute it, and often that tells us the fundamental things. Okay. Thank you very much for your attention. If you are interested in more, you can go to spatstat.org, and there will also be an article in the Australian and New Zealand Journal of Statistics that summarises this.
Thank you very much, Adrian, for that wonderful talk. Based on your performance today, I think if you did start a YouTube channel, you'd have a few hundred subscribers, so go ahead. Do we have any questions for our speaker? Roger, do we have a microphone that we can carry around? No.
Can you just repeat the question?
I'll just repeat the question, okay, and then I'll pass it over to Adrian. Any questions? Oh yes, there's one in the middle. Thomas.
Just a comment. The history of neural networks was that it was impeded by the linearly separable problem. And for many years, a lot of researchers just stopped just because of that result. I see the parallel with your one, the Bartlett one. When they came up with a theoretical result that seemed to be a block, they just gave up for a while.
Yeah.
And then suddenly it caught up, decades later.
Thank you. So,
Yeah, I'll just repeat the question quickly, or the comment from Thomas was that something similar happened with neural networks. There was a sort of people stopped developing methods because they thought it was impossible. Adrian, go ahead.
Thanks, I think that's an interesting parallel. There was a question over here, I think.
Yeah, I was wondering, all of the examples that you gave are from 2D maths. I was wondering if there have been examples where these concepts have taken to 3 or even higher dimensions and actually made a contribution.
So the question is if these ideas have been expanded beyond 2-dimensional point patterns into 3 or 4 or whatever dimensional space.
Yes, I guess so. The software that I developed is mostly for 2-dimensional patterns. That's mainly because I'm lazy. But there are people working on 3-dimensional patterns in particular at the moment. So there's a lot of work on point patterns on the sphere, for example, like locations on Earth, points on a network, so like road accidents on a road network, and 3D point patterns. So that one of the issues there is usually one of the coordinate axes is different from the other two. So if you're looking down a microscope, the axis that represents depth is different from the lateral axes. So it's not just 3 dimensions, it's also that it's not the same as so yes, that's definitely recognized as a challenge, and it's not solved by this particular software, but a lot of the same ideas are being used.
Yeah, we have another question here, James.
Adrian, you mentioned that when you have time as an additional variable, it makes the problem tractable. Is that in some sense analogous to the kind of idea of like discretized, your point process replication could be regarded as discretized time?
So the question is, Adrian mentioned that if you have time, then all of a sudden models can be identifiable. Is that kind of equivalent to having multiple replicated patterns?
Thanks, James. Yes, it is pretty much. So what's happening when you have time, it's natural to think about the current or the future given the past. So the direction of time means you can have models in which the next thing that happens depends on the past history. And then the probability of the whole process is you multiplying together conditional probabilities, and that's a reasonable thing to do. So it's partly about the reasonableness of the models, because of course, 2-dimensional space-time is 3-dimensional space-time, but it's because the models, things that evolve over time, like physical processes that evolve over time, are perfectly natural. And it just happens that all of those, because of the direction of time, they are all tractable. So that's really what happens. But yeah, it's basically because of replication.
Great. I think we had a question in here, Charlotte.
So 175 years on from Jon Snow realising that cholera was probably outbreaking from that central hub, what are spatial patterns going to prove in 175 years' time.
So the question is, 175 years ago, we had the spatial analysis of cholera around the pump. What are we going to have in 175 years in the future, Adrian?
Yeah. Oh, I see. Yeah, good question. Three dimensions, space-time. There are lots of problems that are really. There's a bit of a what shall I call it? A bottleneck happening right now, which is that a lot of the old style methods assume some kind of homogeneity, stationarity or some kind of homogeneity, which is not appropriate, for example, on a network. So if you have a road network and you're analysing road traffic accidents on a network is not homogeneous at all. So a lot of the existing methods don't work. And even measuring the distance from a point on a network to another place is problematic because some parts of the network are more accessible than others. So I think that the problem that's going to take probably another 50 years to wrestle with is what happens if you have some kind of non-homogeneous substrate. It could be that you're living on a network, you're measuring, I don't know, electrical faults on an electrical network, or it could be that if you look into space, you look into the astronomical space, gravity and other effects bend the space. How do we deal with that? So all those kinds of things are currently beyond the ability to deal with in this way. So I think that's probably in 50 years, they'll be better. Does that answer your question?
A true statistician does not predict too far into the future. Yeah. I think, was there another question in the middle somewhere? No, maybe not. Oh, one over here, Rachel.
That plot of the lines of code is very impressive. I want to know if you worked out the influence plot for the lines of code, and if so, what is the most influential line of code?
I'll repeat the question. The question is any line of code out of those 200,000 the most influential? If so, which?
You don't have to.
One of the things I learned from this is there's a lot of people who want to trick the software into doing something it's not designed to do, right? So you say, I write very large help files to explain how things are done, and people want to get around the requirements. There's just some people who have figured out a way to trick my software to do something it's definitely not designed to do and produce a result which is not theoretically correct or like it's not justified. And my favorite example is if you have if you're doing a Monte Carlo test, so you have, let's say, 19 simulations and one data set, then the p-value is a multiple of 1/20, right? So if I want to have a p-value of 0.01, how am I going to do that? Well, there are people who will ask the software to make 19.7 simulations. So there are lots of bits of code to stop people doing that. If you say, how many simulations do you want? No, it has to be an integer. So those are probably the most influential.
Great answer, Adrian. Any final takers? No? Well, I say let's all thank Adrian again for a wonderful talk.